In this research paper, the authors delve into the intricate interplay between the non-Hermitian skin effect, mobility edge, and Stark localization in a non-Hermitian mosaic Stark lattice under open boundary conditions. They employ both analytical and numerical methods to calculate the Lyapunov exponent, phase transition points, density distributions, and spectral winding number. The authors first explore the non-reciprocal Stark lattice with mosaic periodic parameter kappa equals 1. They identify a critical electric field strength that signifies the transition from the existence to non-existence of the non-Hermitian skin effect, which is inversely proportional to the lattice size. This transition aligns with the real complex transition and topological transition characterized by the spectral winding number under periodic boundary conditions. In strong fields, the Wannier-Stark ladder is recovered, and Stark localization is sufficient to suppress the non-Hermitian skin effect. When the mosaic period kappa equals 2, the system exhibits an exact non-Hermitian mobility edge, and the skin states persist even in strong fields, contrasting the gigantic field required to restrain the non-Hermitian skin effect in the kappa equals 1 case. The authors also examine the expansion dynamics of an initially localized state and dynamically probe the existence of the non-Hermitian skin effect and non-Hermitian mobility edge. Anderson localization, a universal quantum phenomenon, is discussed in the context of one- and two-dimensional systems. The authors review the Aubrey-Andre-Harper model, which exhibits a delocalization-localization transition, and its variants that manifest single-particle mobility edges. They also discuss the Wannier-Stark localization, induced by an electric field in a unidimensional disorder-free lattice, and its properties, such as the equally spaced energy spectrum and block oscillation. Here is a refined version of the transcript. The non-Hermitian mosaic Stark model, a unidimensional system described by the Hamiltonian, 1, exhibits non-reciprocal hopping and on-site potential with a mosaic structure. Characterized by nearest neighbor non-reciprocal hopping amplitudes J, E plus or minus G, and on-site potential V_n, which occurs with interval kappa. This model reduces to the Wannier-Stark model when kappa equals 1 and G equals 0. In the Wannier-Stark model, eigenstates are extended or localized depending on the electronic field F and lattice size L. To distinguish extended and localized states, the authors calculate the inverse participation ratio, IPR, of the eigenstates. Under periodic boundary conditions, all eigenstates are extended for f, j less than 2, while they are localized for f, j greater than 2 when kappa equals 1. In contrast, for kappa equals 2, extended states appear earlier, and the system exhibits a mobility edge, denoted by the red solid line in Fig. 1e. The authors also examine the density distribution of the eigenstates for different constant forces f, j. For f, j less than 2, extended eigenstates are distributed over a finite region, whereas for f, j greater than 2, states are localized. Notably, introducing a mosaic structure, kappa greater than 1, leads to extended states appearing earlier, and the system no longer exhibits fully localized phases but mobility edge phases with increasing f, j. Word count 266. In the non-Hermitian Stark model with periodic boundary conditions, the authors develop a theoretical framework for analyzing the properties of eigenstates. The Lyapunov exponent, a key quantity characterizing localization properties, is calculated using the transfer matrix equation derived from the Schrödinger equation. By analyzing the transfer matrix in a quasi-cell and applying matrix eigendecomposition, the authors express the Lyapunov exponent as a function of the parameter E, related to the energy eigenvalue E of the Hamiltonian H. The relationship between the eigenstates of the original Hamiltonian H and its transformed version H is also explored. The transformation matrix S1 is used to convert extended states into skin states, characterized by an exponential accumulation of wave functions at one of the boundaries. For localized states, the wave function is expressed as psi_n, proportional E caret, gamma, nn_0, where n_0 is the localization center and gamma is the Lyapunov exponent for the Hamiltonian H. Numerical results are presented, illustrating the inverse participation ratio versus f, j for different values of the parameter kappa. Visualized in figures, These results demonstrate the transition between localized and extended states as the parameter f, j varies, showcasing the density distribution of all eigenstates for the Hermitian-Stark model under PBC with system size L equals 100. This comprehensive study provides insight into the role of the Lyapunov exponent in characterizing the behavior of the non-Hermitian-Stark model. The non-Hermitian-Stark model with various boundary conditions is a central focus of this research. The energy spectrum and localization transitions are key areas of investigation. Novel ideas and significant findings are highlighted throughout the study. The authors investigate the non-Hermitian-Stark model with open boundary conditions, OBC, and periodic boundary conditions, PBC, to explore the existence of non-Hermitian skin effects, NHSE, and the real complex transition of the energy spectrum. The density distribution of all eigenstates for the non-Hermitian-Stark model with kappa equals 1, shown in Figure 3, reveals that skin states vanish under PBC when the electric field F is small compared to the hopping amplitude J, and the system becomes fully localized when F(J) exceeds 3.3. Under PBC, the energy spectrum of the non-Hermitian-Stark system in the complex plane exhibits real energies when the system is in the localized phase. The critical electric field Fc1 is found to be inversely proportional to the lattice length L, scaling as 1 per liter. To quantify the proportion of complex eigenenergies, the authors define the quantity Fim equals dim, d, where dim represents the number of eigenenergies with a non-zero imaginary part and d is the system size. Numerical results in Figure 4a demonstrate that the critical point of the real complex transition decreases with increasing lattice size L. The authors also introduce the spectral winding number omega to diagnose the transition of NHSE existence under OBC. As shown in Figure 4b, omega equals plus or minus 1, omega equals 0, corresponds to the existence, non-existence, of NHSE, respectively. The winding number omega is calculated using equation 18, with numerical results provided in the inset of Figure 4b. The study reveals that non-Hermitian-Stark systems without mosaic structure still exhibit fully localized phases, and the real complex transition is accompanied by the existence-nonexistence of NHSE under PBC. The critical electric field is inversely proportional to the lattice length, and the winding number omega provides a diagnostic tool for NHSE transitions under OBC. The paper discusses the non-Hermitian mobility edge in a mosaic-Stark model without disorder, focusing on the Hamiltonian described by equation 1, with specific parameters. The energy-dependent non-Hermitian mobility edge is derived as EFC equals 2E, where the eigenenergies of extended states lie in Re, E, less than E underscore C and localized states in Re, E, greater than E underscore C. The system undergoes a mixed phase with a mobility edge when the electric field exceeds a critical value Fc equals P2E, L. The authors consider a non-Hermitian mosaic-Stark model with kappa equals 2 and system size L equals 100, G equals 0.5. They plot the inverse participation ratio, IPR, and the energy spectrum versus F, J under open boundary conditions, OBC, in Figure 5a, showing only real energy spectrum. Under periodic boundary conditions, PBC, all eigenenergies have imaginary parts under weak fields, as seen in Figure 5d. As the electric field increases and exceeds Fc approximately equals 0.23, the system enters a mixed phase with a mobility edge, where the number of localized and extended states is divided by half. The authors also show the real and imaginary parts of the energy spectrum under PBC versus F, J in Figures 5, B, and C, respectively. The energy spectrum in the complex plane under PBC for F, J equals 0.01, 0.1, and 10 are presented in Figures 5, D, F. Notably, when F, J equals 10, the imaginary part of the eigenenergies is very small in the mobility edge phase. The density distribution of all eigenstates for the non-Hermitian-Stark model with kappa equals 2 under both OBC and PBC are demonstrated in Figure 6. The two rows from left to right correspond to F, J equals 0.01, 0.1, and 10. The results indicate that the non-Hermitian mosaic-Stark model exhibits a mobility edge, which is a novel finding in the context of non-Hermitian systems. We delve into the non-Hermitian mosaic-Stark lattice model, focusing on the expansion dynamics of the wave function under open boundary conditions. By examining the eigenstate distributions for kappa equals 2 under open and periodic boundary conditions, we uncover a mixed phase with many body eigenstates for strong fields. In the context of expansion dynamics, we study the time evolution of the wave function, initialized with a single particle at the center site of the lattice. The time-evolved states are determined by solving the Schrödinger equation, allowing us to calculate the particle density at any site and time t. Our results, illustrated in Figs. 7 and 8, show that the system exhibits block oscillations in the extended region. Notably, the non-Hermitian Stark model with kappa equals 1 under open boundary conditions exhibits a phenomenon where the particle moves to the right boundary in the late time evolution, induced by the non-Hermitian skin effect. This effect is dynamically observed in the non-Hermitian mosaic Stark model with kappa equals 2 when f, j equals 0.1, whereas it is absent in the Hermitian counterpart. In contrast, when f, j equals 10, both the Hermitian and non-Hermitian systems are in the mixed phase with many body eigenstates, with the particle localized at the initial site. We further calculate the mean square displacement to estimate the spreading of the wave packet, providing additional insights into the expansion dynamics. These findings highlight the significance of the non-Hermitian skin effect in the expansion dynamics of the non-Hermitian mosaic Stark lattice model. Researchers investigate the non-Hermitian Stark model with electric fields, examining the fate of the non-Hermitian skin effect, NHSE, and many-body localization, MBL, in a disorder-free lattice. By analyzing the time evolution of the mean square displacement, sigma squared, t, under periodic boundary conditions, they reveal distinct dynamical signatures of NHSE and MBL. For the non-Hermitian Stark model with kappa equals 1 and 2, sigma squared, t, exhibits different behaviors. When f, j equals 0.01, sigma squared, t, increases directly to 10 to the power of 3 until t approximately equals 10, corresponding to the extended phase. As f, j increases, the threshold of sigma squared, t, decreases, and the time to threshold reduces for kappa equals 1. In contrast, sigma squared, t, saturates when the system enters the MBL phase for kappa equals 2. The study identifies a critical electric field, FC1, which marks the existence or non-existence of the size-dependent NHSE. Moreover, a weak electric field is sufficient to suppress NHSE in the thermodynamic limit. In the strong field regime, the Wannier-Stark ladder forms, and the localization induced by the field dominates over NHSE, resulting in the Stark localized phase. The authors demonstrate the existence of NHSE and non-Hermitian MBL through the dynamical evolution of an initial wave packet, showcasing distinct behaviors in different regimes. Their work has implications for expanding our understanding of NHSE and non-Hermitian MBL in 1D disorder-free systems. Future studies could explore the extension of non-Hermitian Stark localization in MBL to many-body disorder-free systems, with potential experimental verification in recent electrical circuit experiments. Recent research on mobility edges in unidimensional quasiperiodic systems has made significant strides in understanding the unique properties of disordered systems. This review focuses on three primary models: Aubry-André, optical lattices, and non-Hermitian systems. The Aubry-André model, a paradigm for quasiperiodic systems, exhibits a mobility edge, where extended states coexist with localized ones. This phase transition is characterized by an energy-dependent Lyapunov exponent, which distinguishes between localized and extended states. Notably, the mobility edge is robust against perturbations, indicating the model's relevance to experimental systems. Optical lattices, another class of quasiperiodic systems, have been realized experimentally using ultracold atoms. These systems demonstrate a mobility edge, which is influenced by the lattice's quasi-periodicity and the strength of interactions between atoms. The mobility edge's position and width are tunable, offering a high degree of control over the system's properties. Non-Hermitian systems, which violate the Hermiticity condition, have also been explored in the context of mobility edges. These systems exhibit novel features, such as the coexistence of localized and extended states with different decay rates. The mobility edge in non-Hermitian systems is sensitive to the degree of non-Hermiticity, making it a promising area for further research. This comprehensive review highlights the unique properties of mobility edges in quasiperiodic systems, emphasizing their potential for experimental realization and control. The authors identify key challenges and opportunities for future research, including the exploration of higher dimensional systems and the development of new analytical tools. Non-Hermitian systems exhibit a unique phenomenon known as the skin effect, which has significant implications for topological phases. Previous studies, including those by Jiang et al., Yao and Wang, Kunst et al., Longhi, and others, have explored this effect in various contexts, such as disordered non-Hermitian systems, ultracold datum systems, and many-body localized and thermal phases. Non-Hermitian skin modes are characterized by their localization at the edges of the system, resulting from non-reciprocal hopping terms in the Hamiltonian. This breakdown of the conventional bulk boundary correspondence gives rise to a new type of bulk-skin correspondence, where the topological properties of the bulk are reflected in the edge states. Symmetry breaking and spectral structure play a crucial role in non-Hermitian systems, and the manipulation of the non-Hermitian skin effect can be achieved through external fields. Furthermore, the interplay between non-Hermitian skin effects and many-body localization is explored, with the skin effect influencing the many-body localized phase. The non-Hermitian skin effect also has significant implications for topological phases, as it can lead to the emergence of novel topological states. The breakdown of the bulk boundary correspondence enables the creation of topological edge states that are decoupled from the bulk, allowing for the manipulation of topological properties. In conclusion, the non-Hermitian skin effect is a unique phenomenon that has significant implications for our understanding of topological phases in non-Hermitian systems. Recent studies have sparked significant interest in non-Hermitian systems, with various researchers exploring their properties and applications. For instance, Liu and Xu investigated ergodicity and many-body localization in a unidimensional interacting non-Hermitian Stark system, highlighting the importance of these effects in understanding quantum phenomena. Similarly, Helbig et al. Demonstrated the relevance of non-Hermitian effects in topological systems, showcasing generalized bulk boundary correspondence in non-Hermitian topoelectrical circuits. Experimental realizations of non-Hermitian skin effects have also been achieved in electrical circuits by Liu et al. And Jiang et al., showcasing the potential of non-Hermitian systems for novel device applications. Furthermore, Su et al. Developed a platform for simulating non-Hermitian disordered systems using linear circuits, enabling the exploration of their properties. These studies collectively emphasize the significance of non-Hermitian systems and their potential to revolutionize our understanding of quantum physics and device design.